It's math time with Heinz. It's math time with Heinz. Math time.
Hi everybody, in this lesson 1 here, we're going to be looking at the multiplication of polynomials. So Unit 1 is all about these things called polynomials, and we're going to first start by reviewing how we can multiply them, which we learned about back in Algebra 1. So in this lesson, we're going to be multiplying polynomials. So before we get to working with polynomials, let's work with plain old numbers. So show that 28 times 27 is 20 plus 8 times 20 plus 7 using an area model. So going back to like 3rd grade in elementary school when you first started learning about multiplying, we multiplied using area models. And here's what we're going to do. We're going to find the area of the square. We're going to find, or a rectangle in this case, we're going to find the area of a square whose side lengths are 28 times 27. So I know this might be different that we're using this side of the square here, but that's the side of the square we're going to use going forward. So 20, now all we have to do is find the area by finding the product. 20 times 20 is 400, 20 times 8 is 160, 20 times 7 is 140, and 8 times 7 is 56. So now we can find the area of, we can find the product, 28 times 27, by finding the sum. 400 plus 14, that's plus 300, plus 56 gives me 756 is my product. So I found the area of 28 times 27 by finding the product of these two binomials, 20 plus 8 and 20 plus 7. And we end up getting 756. So using the same idea, let's use the tabular method. The tabular method means use a table, find the area, it's the same thing as the area method, to multiply x plus 8 times x plus 7. So I'm not using integers anymore, I'm using polynomials. these are in the case called binomials because there's two terms. There's two terms, so they're called binomials. And explain how this, okay, we'll get there later. Let's first find the product. So I'm going to make my area model. I'm going to make my table and put x plus 8 and x plus 7. Now here's the thing, don't put this plus on the side in the middle here, it goes with that second term there. So here's the question, what is x times x? Is it 2x or is it x squared? So repeated multiplication, x times x, is what exponents are all about. Exponents are all about repeated multiplication. So 8 times x is 8x, x times 7 is 7x, and 8 times 7 is 56. So I find the product, kind of like if I was doing a Punnett square from biology, to find what goes in each box. So this tells me x plus 8 times x plus 7 is actually what? So look here. How many x squareds do I have? I have 1x squared. How many x's do I have? Notice how they're on the diagonal there. 8x and 7x gives me 15 x's. And then I have that 56 there. Then I have that 56. So this product, I've just said a sentence of equivalence. I said x plus 8 times x plus 7 is equivalent to, that's what equals mean. It's the exact same thing as this trinomial here. This is a trinomial because tri means 3. I have 3 terms there, x squared plus 15x plus 56. Hopefully this seems familiar. We are going to be using tables a lot throughout this course, especially in the beginning of the year. So how do we do it without a table? Maybe your 9th grade or your algebra teacher didn't tell you how to multiply without a table. And the answer is our friend, the distributive property. What this table is really doing for us is we're just nicely applying the distributive property. Our second favorite property, the distributive property, which we use a whole lot in algebra. So here's what we do is we take this first term here, that's a bad color to use, need a lighter blue. We take this first term and we distribute it to that monomial. So we get x times x plus 7. Then we take this second term here and distribute it to that binomial. So plus 8 times x plus 7. So we take each term from our set of parentheses and distribute it to the entire polynomial. And then we distribute again. I get x squared plus 7x I get 8x plus 56, and wait a minute, I've seen these exact four pieces before. X squared, 7x, 8x, 56. X squared, 7x, 8x, 56. What the table does, what the tabular method does, is it lets us nicely organize the distributive property. And then we finally combine like terms one more time. How many x's do I have? I have 15 x's plus 56. My circle there blocks numbers. So there we go, x squared plus 15x plus 56. That's how we can safely use the distributive property. But use a table. Use a table because tables are going to get bigger and wider, so it's going to be a lot cleaner to just use the tabular method. So use the tabular method to multiply this trinomial and this trinomial and combine like terms. So if you're up for it, pause the video right now and see if you can find that product on your own. If not, I'll walk you through it right now. So pause the video if you feel confident and check your work with mine, or you can just keep watching and we'll go from there. So notice I made a much larger box because I have x squared plus 3x plus 1 on the top, which means I need 3 columns going down. I need 3 columns going down there because I have a trinomial. I start with a 3-termed polynomial. And on the side here, I have x squared minus 5x plus 2, which means I need 3 rows. Notice, key thing here, that I kept that negative with that 5. I don't have a floating negative sign in the middle there. That negative went with the 5. And now we just multiply. X squared times x squared gives me x to the 4th. 3x times x squared is 3x to the 3rd. 1 times x squared is x squared. All I did there was I distributed x squared into that whole trinomial there. And now we're going to distribute again. Let's take negative 5 and multiply it through. Negative 5x to the 3rd, right? X squared and another x bumps my exponent up 1 because I have 3 x's being multiplied together there. 3x times negative 5x is negative 15x squared. 1 times negative 5x, well, we can all do that. That's negative 5x. And finally, the easiest point of this whole thing, now we need to multiply by 2. 2x squared, 6x times 2. Now what we need to do is combine like terms. And the way that we're going to combine like terms is we're going to check on our diagonals. We're going to check the diagonals of these boxes here and notice that all of our like terms happen to be lying on the same diagonal. What do I mean by that? I mean that all my x to the 3rds were on that blue diagonal there. All my x squareds landed on this orange diagonal here. So what this tells me, if I multiply, if these two factors multiplied together, what happens when I multiply these two factors together? Will I get x to the 4th? How many x to the 3rds do I have? Now is when we add. So the first step is to multiply. The second step is to add/subtract to combine your like terms. Negative 5 and 3 makes negative 2. I have 2, negative 15, and I remember there's a 1 there. I have 1x squared. 2 and negative 15, I have 1 plus 2 is 3, minus 15 is negative 12. That took me longer than it should have. Then I have 6x and negative 5x. Well, 6 minus 5 is 1. You don't need to put the 1 there, but you could. Then I have the 2. So this product is the answer for when I multiply these two factors together. When I multiply those two factors, that polynomial there is my product. Well, let's do it again. Use the tabular method to multiply these two together. Here we go. I can do this. X squared plus 3x plus 1. So I have 3 columns. And x squared minus 2. X squared minus 2. So I have 2 rows. And now we just find the product. Here we go. X squared times x squared is x to the 4th. 3x times x squared is 3x to the 3rd. 1x squared is just x squared. Now I'm going to distribute through this negative 2 into this trinomial. That gives me negative 2x squared, negative 6x, negative 2. And now you just said, hey coach, you said I could just look at the diagonals, but if I look at my diagonal here, notice that they're not like terms. So let's finish up this problem and then we'll talk about why that happened. And that's going to be important for when we go forward into the future lessons that we're going to do with multiplying and dividing polynomials. So let's just get the answer first, and then we'll deal with the fact that that diagonal didn't match up there. So I have x to the fourth. How many x to the thirds do I have? Well, I only have 3 of them. This is my only x to the third term. But do notice I have a couple x squared terms there. 1 minus 2 gives me negative 1x squared. There's no other x's, and that's the only plain old number. So that's my answer. These two factors, the product of these two factors gives me this, this 5-term polynomial here. So why didn't that happen? Why didn't these diagonals match up here? And I'll give you the hint. It has to deal with what's going on over here. Pause the video, see if you can think what's going on over here with this x squared minus 2x term. Pause the video, see what you think's happening. So hopefully, maybe you noticed something's missing. Someone's missing in here. What normally comes after an x squared term is a plain old x term. But this binomial here doesn't have a plain old x term. It has 0 of them. And then the constant term comes. So when we work with polynomials, there's always this order, this standard form, which we hopefully remember from Algebra 1, where we start with the highest power. So let's say we start with x to the fourth. Who comes after x to the fourth? Normally it's x to the third. Who comes after x to the third? X squared. Who comes after x squared? Plain old x. Who comes after plain old x? The constant, the plain old number. So because this guy's missing his x term, this binomial is missing the x term, the diagonals didn't line up, and that's going to be really important going forward. For multiplying, you just got to be a little bit more careful when you start combining like terms, but when we start dividing, we're going to need to have everybody in standard form, so that we're going to be throwing in these 0 x's when we start dividing polynomials. Use a distributive property, I'm going to say or tabular, I'll throw that at you there, or the tabular method, to find this product in standard form. So let's find the product of x minus 1 times x squared plus x plus 1. I'm always a fan of having my tables more horizontal than I do vertical, so it doesn't matter. You could have a more vertical table with 2 terms at the top, but that's not what I usually do. I normally keep my tables more horizontally oriented. So x squared, x, and then a 1, then I have an x minus 1 here. So we multiply x squared times x is x to the third. X times x is not 2x. Stop doing that. X times x is x squared. 1 times x is x. Negative x squared. Basically everyone becomes negative. So the product, x minus 1 times x squared plus x plus 1, what does this product come out to be? Well, I have x to the third. Well, I have 1x squared and negative 1x squared, which those cancel out is not really a thing. Those add to 0. Cancel out is not a mathematical operation. 1 minus 1 makes 0. So these guys add to 0, so we're going to say goodbye. Goodbye, goodbye. 1x and negative 1x, those guys also add to 0. Goodbye, goodbye. And I'm left with a negative 1. So that right there is my product. It's in standard form, but remember, there's some people missing. There's 0x squareds, there's 0 x's in this polynomial. Hopefully this is all coming back to you right now of how we multiply polynomials, because we did do this in 9th grade. Pause the video. See if you can try this one on your own. Find the product of x minus 1 times x to the third plus x squared plus x plus 1 using the table. See if you can do it on your own. Pause the video and we'll come back and try it. So notice I made my table extra long this time because I noticed I had a 4-term polynomial here that I had to work with. But I only have 2 on the side. So here we go. X to the fourth, x to the third times x. X squared times x. x times x is x squared. Everybody kind of bumped up a level in terms of their exponent there. Now I'm going to distribute through a negative 1. So negative x cubed, negative x squared, negative x, and negative 1. So what does this product equal? When you multiply it, well, let's check our diagonals. And wait a minute. Goodbye, goodbye, goodbye. All those terms dropped out there. They all added to 0. So what we end up with is this product actually comes out to be x to the 4th minus 1. X to the 4th minus 1 is my final answer there. But this problem looked really similar to this problem we did right here, where these middle terms were adding to 0. So let's make a generalization here. Let's generalize. That's what we do in mathematics, is we look for patterns and we say, wait a minute, this looks familiar. How can I kick it up a level? So using exercises 4 and 5, generalize the pattern that emerges for this identity here. So an identity is something that's always true. An identity is a mathematical statement that is always true. So what is all this saying here? So for any positive number n, what happens when I multiply them? So let's pause a second. Let's say I actually gave you this problem. X to the 7th, x to the 6th. Well, what's this dot 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 means? The dot 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 means keep going. What comes after x to the 6th? X to the 5th, x to the 4th, x to the 3rd, x squared, x, and 1. So if I was to multiply that, using these two previous problems as a generalization, right? X cubed, x squared, x, 1. This time I'm starting with x to the 7th. What do we think our answer is going to be? X squared, x, 1. Notice all the middle terms are going to drop out, and we're always just left with the first term and the last term there. We're always just left with the first term. In this case, that product would be x to the 8th. And then all those middlemen would drop out, and we're left with a negative 1. So in general, if I have x minus 1 times x to the n, 1 smaller than that, if I had just a whole bunch of x's where all their coefficients are 1, and I have every power in order, what does that product come out to be? Well, all those middle terms are going to drop out, and what happened to our exponent? This one became x to the 4th. So I was x to the n, so it gets kicked up to x to the n plus 1, and then I end up with a negative 1. So right now, this identity helps me realize if I'm doing a problem and I say, wait a minute, I see this right here, x minus 1 times x to the 9th plus x to the 8th plus x to the 7th and blah, 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 blah. I can quickly say, wait a minute, I know this pattern. I've seen this pattern before. It becomes x to the 10th minus 1. I quickly did that because I have this generalization. I made sense, and I look for patterns in repeated reasoning. One more problem to end out the video. That's hard. I'm not going to ask you to do that much, but I want us thinking a little bit. I want us to be a little bit more mathematical than just doing problems over and over again. Last problem of today, create an equivalent expression to a plus b plus c squared. Well, what does squaring mean? Well, squaring means I'm going to multiply something by itself. I'm going to find the product of itself with itself. Well, it's 3 terms times 3 terms, so let's make a big box here. A plus b plus c times a plus b plus c. I have a 3 by 3 grid here for multiplying. A times a squared. B times a. Normally we put letters in alphabetical order. A times c, ac. A times b, b times b. C times b. And finally, we're going to distribute through this c now. AC, BC, and c squared. Well, there's things to combine here, and this isn't a standard polynomial in terms of x. So the way we write this answer, there's not a standard way to write it. But what I could write is I could write a squared, I noticed b squared, I did that, plus c squared. And then let me deal with these guys. Those guys repeat. AB and AB, I have 2 of them. I have 2 ABs. I have 2 ACs, and then I also have 2 BCs. So that would be my product. That answer is not pretty, but that is the product of these expressions here. So at this point, that's lesson 1 of Algebra 2. We multiplied polynomials, and in lesson 2, we're going to do this all backwards and divide polynomials. I'll see you in the next video. If I can end this one. Let me see if I can end this one. There we go. Here's our ending slide.